Hey, Physics 111. All right, so I'm going to do hopefully maybe 1 or 2 videos on Chapter 12, and then maybe a couple on Chapter 13. So Chapter 12 is static equilibrium, and we already did some of this in class last week, so I'm just going to be going over a little bit, and then I'm going to do some examples, which are really the best way to learn how to do these problems. So static equilibrium is when we have a situation where we want an object to stay still, completely still. We don't want it to move at all. We don't want it to move up and down. We don't want it to move side to side. We really don't want it to spin around or even partially spin. Examples are, bridges or buildings or even furniture. You want your furniture to be stable. You don't want to sit on it and have it tump over. You don't want to have it, move around easily most of the time. And so many, many, many things are in this state, which we call static equilibrium. In physics terms, if something is not moving at all, we would say that its accelerations are zero. So overall, its acceleration, which is a vector, is zero. But what that really means is, of course, is that the x acceleration is zero and the y acceleration is zero. And the z acceleration is zero, which of course means that the f nets of x, y, and z are zero. So when you add up all the forces, and there will be forces acting on our object, but when you add them up, they're going to be equal to zero. And then if we also don't want it to spin, right, no spinning, that means that alpha, the angular acceleration is also zero, which of course means our net torques are zero. So when you go through and you actually do a problem, like we're going to do, of course, because it's physics, we're going to do problems with this. They're going to be math problems, and they're going to be both force problems, where we talk about F nets all adding up to zero, and there'll also be torque problems, where we have the torque nets, the torques adding up to equal zero. In the lab we did last week we had torques. We had 2 or 3 torques, and they added up to zero. We didn't have to deal with forces. Now we really have to deal with both. And so we're going to follow these rules for static equilibrium. It's very similar to the rules for forces problems, but now we're going to have both forces and torques with some simplifications because now all our accelerations are zero. I uploaded that rules for static equilibrium is under the chapter 12, 13, and 14 practice problem announcement on our OAKS page. It looks like this. Here it is. It's a little longer than the rules for force problems because we both have force parts and torque parts. And I'm just going to follow these rules as I do some example problems. Needless to say that much like force problems, the majority of credit for the work that you would do here, the credit on, say, a quiz or an exam, is not going to be the number at the end. It's going to be the going through these steps and coming up with the equations that you need to have to do this. So, getting the equation is really the physics, and showing me how you got those equations is the physics, and that's what I'm testing you on. So let's look. So number 9 is one of the first problems. I think you guys are doing number 6, but number 9. I think number 6, if you follow the steps, hopefully you can do the other one. So number 9, there's actually a lot of information in these 3 sentences. It says, a meter stick balances horizontally on a knife edge at the 50 centimeter mark. So what that really is telling me, all right, so I'm going to draw this just briefly. So it's just a regular meter stick, and it tells me that at this 50 centimeter mark, if I put this here at half a meter, if I put something there, it will balance. It will be balanced. That tells me that the center of mass of the meter stick is at that location, right? The center of mass of the meter stick on its own is at that location. Otherwise, it wouldn't balance. So this is because it balances at this location. So that's what this first sentence is trying to tell me. Now that we know that, it says, okay, they take that same meter stick and they tape or they stack 2 5-gram coins at the 12 centimeter mark. And then they find that they can balance the stick now at 45.5 centimeters. All right, so, and they want to know, what is the mass of the meter stick? So here we go. Let's look at our rules. It says, first we're going to follow the rules for force problems. Below, these are slightly changed for this type of problem. It says, number 1, draw a long, skinny rectangle. And so this is different. So this is just sort of our pre-information that gives us this information right here. But now we're really doing our problem. So I'm going to redraw my long, skinny rectangle, and that represents my actual object that I'm dealing with. In this case, my meter stick. Now it says, draw arrows with the tails touching the rectangle for each force acting on the object. Try to draw the arrows showing where on the object the forces are acting. So if I put 2 5-gram coins at the 12 centimeter mark, let's pretend like this is the 0 and this is the 100, or 1 meter, and 0 meters as it's shown there. So at the 12 centimeter mark, that means that roughly around here, there's 10 grams, right? There's 0.01 kilograms times G pushing down at that location. So the mass here is 0.01 kilograms, or 10 grams. And this is 12 centimeters from here to here. Let's blow that up a little bit. So from the end of this to here, that's 0.12 meters. Then there's also, it tells me, I just blew it up so we can't see it. It says that when I do that, I can balance it at 45.5 centimeters. So that means that over a little bit. So now I have the balance here. So I have something I'm holding up at this location. That actually means that there's a normal force there, right? If I'm holding it, then there's a normal force up on my meter stick at that location. And this is at 0.455 meters from the end. All right, it tells me it's at 45.5 centimeters. The last thing, and there is another force, it tells that the center of mass is at half a meter. So it's right here. The center of mass is the location where the gravitational force of the meter stick acts. So this is where the mass of the meter stick times G acts, where mass of the meter stick. And this is what I'm actually trying to find. And again, this occurs at half a meter away, right? I'm running out of space. But this is from here to here, that's half a meter. And I'm trying to find the mass of the meter stick. So I have 3 forces. I have the gravitational force on the 10 grams. I have the gravitational force of the meter stick. And then I have the normal force at the actual pivot or balance location. So those are number 2. Draw arrows with the angle, with the arrows touching. Try to draw the arrows where on the object the forces are acting. Decide how many dimensions the problem has. Only X, only Y, both X and Y. Well, here I only have up and down vertical forces. So I only need Y plus Y. Again, the arrows don't touch, just like with the force problem. And then normally in number 4, we would write out what the accelerations were if we think that it's accelerating a certain direction or whatever. But this is an equilibrium problem, so our A sub Y is 0. All right, so now, just as we did before, we can go through and write an F net Y equation. So I'll write that over here. I'll say, okay, F net Y, actually I'll do it down below. So F net Y, I have the normal force up. I have 0.01 kilograms times G, and I have the mass of the meter stick times G. These are my three forces. Normal is up, gravitational force of the 10 grams is down, gravitational force of the meter stick is down. This has to equal 0 because A sub Y is 0. F nets are 0. So now I have this equation. It says that, the normal force is equal to, this stuff here, but I don't know the mass of the meter stick. So I'm stuck. So now we go down to the second part of our problem, where we deal with the torques. It says, number 1, pick the axis location. It will be impossible to do this without an axis location. Sometimes it's obvious and sometimes it's not. In this case, the axis, again, the axis is the location amongst where the thing would pivot or rotate. Well, it would pivot here, right? This is our pivot location. This is actually where we put it. This is our axis. So in this problem, it actually is obvious where the axis is. So that's going to be my axis, and you want to kind of label it. It would be really helpful to me to see that you label it. We'll come to the second part. If you don't know, if it doesn't give, you don't have an axis location, it's not obvious, the problem doesn't tell you where to choose the axis, then we'd want to pick a place specifically based upon the forces that we've got. But we'll do that in the next example. All right, so number 2, for each force, not component of a force, but each force, determine the torque from that force using this equation, where torque is equal to R, where R is the distance from the axis where the force is acting, F is the magnitude of the force, theta is the smallest angle between R and F, and then we're going to determine if the torque is counterclockwise or clockwise. So I'm going to go ahead and just start here on the left. I'm going to say, okay, my first torque is the torque from the 10 grams. Now, from the axis to here, right, from the axis to here is going to be 0.455 minus 0.12. So the R for this is 0.335 meters. Right, this is 0.335 meters from the axis to the location where this force acts. The amount of the force is 0.01 kilograms times G. The angle from here, from this R to the force, is a 90-degree angle. And then on its own, this force would cause this meter stick to move counterclockwise. I'm going to actually get a number for this. So 0.335 times 0.01 times 9.8, the sine of 90 is 1, and so I get a torque of 0.03283 Newton meters, and again, it's a counterclockwise torque. All right, let me move to the next force. This is the force from the torque from the normal force. This happens at a distance of 0 meters from the axis, and so it's a 0 torque. Right, at the actual pivot point, the distance from the pivot point to the force is 0, so there's a 0 torque. And the last force is from the mass of the meter stick. Now this happens at 0.5 meters, but that's 4.5 centimeters from the axis to our force. Right? If this is at 0.455 and this is at 0.5, then this is 4.5 centimeters from there. The amount of this force is the mass of the meter stick times g. This is also a 90-degree angle, but this is a clockwise torque. On its own, this force would cause the meter stick to move clockwise. So that's what we're supposed to do in step 2, is for every single force I've drawn in my free body diagram, I now go and say, what's the torque? What's R? What's F? What's theta? Is it clockwise or counterclockwise? And I write them all down. Step 4, sum all the torques by adding all the counterclockwise torques and subtracting all the clockwise torques. So now I say, all right, torque net, I'm going to take my counterclockwise torque and I'm going to subtract my clockwise torque, and then these sum up to 0. Net torque is equal to 0. So my counterclockwise torque is this one, 0.03283 nanometers. 0.03283 nanometers. My clockwise torque is from the meter stick, mass of the meter stick, g, right? Sine of 90 is 1, and that has to equal 0. So now I can actually use this to straight up solve for the mass of the meter stick. Right? I'm going to get that the 0.03283 nanometers divided by G and 0.045 meters divided by 9.8 divided by 0.045, and the mass of my meter stick is 0.0744 kilograms, or 74.4 grams, which is actually pretty similar to some of the meter sticks we had in the lab. Once I know the mass of the meter stick, I can actually go back and use this equation to determine the normal force if they asked me for that. Remember, this would have been the 0.010 kilograms times G plus the mass of the meter stick times G. Which would have given me a normal force of 0.828 newtons. Technically, we probably could have pulled this one off without doing the force part of it, but it's always kind of a good idea to do the force part. Let's look at one where we can't get away with it without actually doing the forces as well. You know what? I may save this for part 2.